Section 14 of The Science History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in January 2016. The Science History of the Universe, Volume 2, edited by Francis Rolt-Wheeler. Geology. Chapter 7, Diastrophism, Part 2. A great earthquake usually begins suddenly and without warning. A rumbling sound, quickly becoming a loud roar, accompanies or slightly precedes the movement of the ground, which is at first a trembling, then a shaking, and finally a rapid swaying, wriggling motion, describing a figure 8, which is extremely destructive and overthrows the buildings affected, and even in the open country it is impossible to keep one's feet. The surface of the ground has been repeatedly observed to rise in low, very swift-moving waves, somewhat like those on the surface of water, upon the crests of which the soil opens in cracks, closing again in the wave troughs. When the earth waves traverse a forested region, the trees sway violently from side to side, like a field of ripe grain in the breeze. In the details of movement, earthquakes differ greatly from one another. Sudden and extremely violent vertical shocks may come from below, or the surface may writhe and twist in every direction, instead of rolling in waves. There may be only a single shock, or many successive ones. Strictly speaking, the geological effects of earthquakes are of less importance than is usually supposed. The violent shaking of the surface often brings about great landslips in mountain regions, which precipitate enormous masses of earth and rock from the heights down into the valleys. In all of the more violent quakes, cracks and fissures of the ground are formed, which may close again or remain open, and may show a lineal, curved, zigzag, or radiating arrangement. Through these fissures great quantities of water and sand are often forced up from below, and form little sand craters or water-filled funnels on the surface. Frequently the fissures assume the character of faults or dislocations, one side being raised, the other depressed, so that long scarps or low cliffs are left standing. In the San Francisco earthquake of 1906, two long lines of parallel faults were formed, with varying throw up to 20 feet. A very common result of earthquakes is a change in the circulation of underground waters. Wells and springs go dry, while other springs are formed in new places, or old ones may be increased in volume. The changes in the form of the land surface produce corresponding changes in surface drainage. Rivers are diverted into new channels or dammed into lakes, while streams intersected by fault scarps form new cascades. The recent earthquake, which occurred at the extremity of the Italian peninsula, was at first seismologically explained as the propagated effect of a fault slip. It was not the eruptive outburst of Etna, according to Sir Norman Lockyer, that set the earth quivering in the vicinity, but the prolonged tension of the crust, a sudden snap, an abrupt settlement, and then the waves of the quake. The celebrated geologist, Professor Edward Suess of Vienna, expresses himself very pessimistically regarding the outlook for the near future. According to his theory, the Calabrian and Sicilian shocks do not result from volcanic outbreaks anywhere, but were occasioned by a general sinking. Should this settling down continue, further catastrophes are likely to ensue. In studying the causes of earthquakes in general, they are usually divided into two classes, volcanic and tectonic, though it is often impossible to determine to which of the two classes a given earthquake should be referred. The volcanic earthquakes, which are closely associated in time and space with volcanic eruptions, are due to steam explosions and to the struggles of the rising lava within the earth to escape. Tectonic earthquakes are believed to be due to stresses in the interior of the earth, which, when suddenly yielded to by the rocks, cause the jar and shock which generates the earthquake. No entirely satisfactory hypothesis has been advanced to account for the origin of the stresses referred to above. The explanation usually accepted is that the earth is slowly contracting on account of the loss of heat, and that the crust, which must follow the shrinking interior, is being crowded into a smaller space, with resultant ruptures and shocks. On the other hand, it is contended by some geologists that all earthquakes are essentially volcanic in origin. The stresses induced by the changing of the Earth's axis also has been put forward as an explanation. Many geologists attribute the recent earthquake at Messina to the explosion of steam, according to the theory just given prominence by Dr. T.J.J.C. of the Naval Observatory on Mare Island, to the effect that all great earthquakes are caused by the explosive force of steam generated by the percolation of seawater to the molten or red-hot rocks far below the Earth's surface. He asserts that the so-called waves following great earthquakes are not really tidal. They are produced by seismic disturbances of the sea bottom and should be called seismic sea waves. A seismic wave, explains Dr. C., is due to a sinking of the sea bottom at some distance from the shore. When this happens, the water, of course, flows in from all sides to fill the depression. Then, when the currents meet at the center and raise a ridge by their mutual impact, the ridge collapses under gravity and sends the first great wave ashore. Where the ridge of water once was, he says, a second depression in the sea level is thus developed. The water again flows as in the first case, and the process keeps on repeating itself. On June 15, 1896, the northern shores of Japan were visited by terrible earthquake shocks, which were recorded on seismographs in Europe. The disturbance originated beneath the Tuscarora Deep. This oceanic abyss, which reaches a depth of 4,600 fathoms or more than 27,000 feet, is known as the worst earthquake region in the world. On the Japanese coast, as on that of South America, the water first withdrew from the shore and later returned in a great wave. Along a region 70 miles in length, the coast villages were washed away and 30,000 people perished from the earthquake and the inundation. In other instances, the water rises suddenly, overflows the coast, and washes ships inland without any previous withdrawal from the shore. For instance, on December 29, 1854, the city of Shimoda in Japan was overwhelmed by a sudden inrush of the sea about an hour after a violent earthquake. Seismic waves of this class are produced by an upheaval of the sea bottom, which lifts the overlying water bodily upward, causing it to rush in upon the shore. In summing up, Dr. C says that the so-called tidal waves that follow violent earthquake shocks are due either to the sinking or to the elevation of the sea bottom, and that earthquakes themselves are due to the secular leakage of the ocean bottoms. The great depth and the enormous pressure of the seawater, with the aid of capillary forces, drive it through the rocky crust of the earth till it comes to the intensely hot strata some 20 miles below the surface. The earth in many places is at a high temperature inside, and steam develops under the crust. When the pressure of the steam accumulates, it finally shakes the solid crust until it gets relief through some opening. Practical people, notably insurance companies, are asking the scientists whether seismic disturbances have not a common and determinable origin, and if their cause can be ascertained, if they will ever be able to foretell their occurrence. They are questions which are being carefully considered, notably by Professor H. H. Turner, who in a recent paper on the times and places of earthquakes is somewhat pessimistic. It has been noted that some 30,000 shocks are detected annually by the recording instruments. Of all these, only 60 are world-shaking and observable from a distance. The two rings which the earthquake districts make when plotted on the globe also has been referred to. Professor Milne and others attach peculiar significance to this geographical distribution. Now, this is not merely a convenient geographical summary, but a physical fact of virtual importance, according to recent researches by Professor Jeans. In a remarkable paper read before the Royal Society, he gave reasons for believing that the Earth is not so absolutely a sphere or spheroid, but is slightly of pear shape. Under gravitational stress, it is continually approaching the spheroidal form. The pear is being crushed into a sphere by its own attraction, and the result is a series of earthquakes which will naturally occur in the weakest places. The speculation, for it is little more as yet, possesses no small degree of interest. Also, Professor Turner, dealing with the distribution of earthquakes in time, suspects that there must be a direct connection between polar movement and the strain on the crust of the Earth. For many years it has been observed that there are slight but irregular changes in latitude, or, in other words, the axis of the Earth does not always point in the same direction. The world top is not spinning truly, but it wobbles slightly. When the change in direction of its axis is sharp, large earthquakes have been frequent. If a swiftly moving body is, so to speak, compelled to turn a corner, that it should be subjected to strains which might result in yielding is easily conceivable. A shifting of the Earth's axis, even to the slightest degree, would impose a great strain upon some parts of the Earth's crust, and this might explain earthquakes and in turn lead to appreciable results in foretelling them. But, to use the words of Professor Simon Newcomb, earthquakes are due to a shifting of the Earth's strata, but what causes that shifting is not positively known. The general theory hitherto has been that the shifting is due to the gradual lessening of the Earth's surface. That may be a fallacy, but Professor Milne has yet to establish his hypothesis. Nevertheless, the great prestige of Sir Norman Lockyer's name has been given to the Milne theory, that is, that the earthquake is a natural phenomenon resulting from the failure of the Earth to swing true upon its axis. The great seismic disturbances of the past few years tend, this expert thinks, to support the theory advanced by Professor Milne. This would yield the inference that it is possible to calculate the frequency of earthquakes in the light of their suspected cause. However much announcements of this nature may appeal to the scientific mind, says Professor Milne, the layman requires something more definite. If not to the minute, he would at least like to know the day on which an earthquake is to occur. The science of seismology may never become so precise as all that, but when the factor of causation is given, when it is known for certain whether or not the sun spots or the shrinkage of the globe or the alteration of the direction of the Earth's axis must be given credit for the earthquake, the chief problem of the seismological prophet will have been practically solved. End of section 14.